So welcome to this new video where we're going to study the embedded system development with the Altera Intel Design Suite. We will learn the basic principle of this piece of software that is proposed by Intel, and we'll learn how to build a full system based on the Nios 2 processor. One of the most important parts of this methodology and the tools is the QSys tool. This tool allows designers to build a full system at a very high level of abstraction. It means that designers only have to provide the architecture of the system by building this system with different IPs that are available in a library and just connect them very easily in software. QSys, or previously SoPC Builder, automates IP connectivity, which is very useful to designers because they don't have to take a long time to take care about the interconnect. Everything is taken into consideration directly by the tool. Once the system is completely built, QSys automates HDL generation, meaning that it will generate all VHDL and Verilog files that are going to describe the full hardware architecture, the processor, for example, but also the peripherals. These VHDL or Verilog files will be later provided to other tools like Quartus at Intel to take care of the hardware design implementation. The fact here that we are working at high level of abstraction increases productivity. It's very easy to build a full system within a few minutes and then click on a single button to generate all hardware description files. You will see that in the lab, which is associated with this course. So, that software tools make it possible to go from the concept to a real system in a very short time. The first step here is to have an idea of the architecture that we want to design. This is obvious. In this case, designers may want to draw some schematic very rapidly where they can build their system with a microprocessor and the associated peripherals. They also need to have an idea on how these components are going to communicate with each other. For example, through a bus or other dedicated interfaces. This corresponds to step 1. Once this work is completed, it's also very easy to go to QSys or Platform Designer or SoPC Builder, which are the same kind of tool, and enter the corresponding design in the tool. Designers may choose components within a library and build a full system. This corresponds to step 2. Once everything is described in software, then designers just click on a single button to generate the different files and quit QSys. The generated files can be used in the hardware description following the classical design flow in Quartus. For example, it's possible to simulate the architecture using the functional simulation first, using ModelSim, for example. Then the classic design step, such as synthesis, place and route, are performed nearly automatically. An additional timing simulation can also be performed to take into consideration all the timing, delays, etc. If all constraints are met, then designers may generate the programming file that is going to be downloaded into the FPGA. So the bitstream file has the .sof extension in the internal environment. You will see that later in the lab. Here is an example of the QSys GUI interface. The main application is divided into several sub-windows, as depicted here. A first window with the number 1 is composed of all available IPs that designers may use to build their architecture. A second window, here, corresponds to the clock settings table, where you can enter the clock properties, for example, the clock frequency. The third window is the main active window, which contains the description of the architecture. It is very easy to build the architecture by dragging the components from the first window to this active window and make the connections between the different components. These connections may be provided by a fourth window, which is called the Connections panel. This is very easy to create a specific connection between components by simply clicking on the mouse, as we will see later. Here is an example of a full system where you can find different elements. The blue elements are components that were taken from the library. For example, we have the processor, an EOS 2 processor on 32-bit, an Ethernet bus master, a UART interface to communicate with the external world, and SPI and PCI interfaces. There's also a DDR2 controller for memory management. It's also possible for designers to generate their own custom logic component, which means that they can describe a specific component in VHDL, for example, and include this component in their system. Some other components are also completely generated by the tool itself. This is the case of the address decoder, for example, which is used to generate the proper addresses for each peripheral. The bus arbiter is also automatically generated, and all connections that we call glue logic are also automatically generated by the tool. So it's completely transparent to designers that do not need to worry about that stuff. This considerably reduces the design time of architectures. Here we show that it is possible to get a lot of IP cores that are available in the library. Over 50 IP cores and components are available in software by default. For example, you can find a lot of interface protocols, but not only. You can find memories, memory controllers, various peripherals like parallel input-output, buttons, LEDs, LCD screens. But you can also have dedicated IPs for communication, for example, as well as video and image processing blocks. It's also possible to enhance the library by adding your own custom device, as we will see later in this course. This is also a specific exercise that you're going to do with an EOS 2 processor during the lab. Here is the glue logic connection panel. This is a small window composed of different wires, as you may see here, which correspond to the different types of buses. You can find the instruction bus, the data bus, but also additional buses to connect the different components between each other. A connection is effective if a circle here is black, okay, and no connection means that there's a white circle instead. This is very easy to make a connection between different components and very quick with a few mouse clicks. You can connect a specific component or specific inputs to the data bus or instruction bus, or even to a specific clock signal within a few seconds. This is a very important slide. It shows the different generated files from the QSys software. The first type of generated files are the hardware description files. They contain the hardware description of the full system. They not only describe the internal functioning of the different components, like the processor or different peripherals, but they also contain the description of all the interconnections between these components. These files are in general Verilog or VHDL compatible and can be directly used by the Quartus software as any hardware description circuit. The second type of generated file is called the SoPC info file, which corresponds to a system description file, and in this file, a description of all components with their versions is performed. This file is going to be used in another tool for software development. This is going to help building the different drivers to manage the different peripherals that are included in the design. It will also be used to generate the different functions that can be provided by the programmer to access hardware. To summarize, QSys is the key component of the methodology because it can generate the hardware description of a full system based on the microprocessor, as well as another file that is going to be used to build the proper libraries and functions to manage hardware. Now we're going to talk a little bit about how designing a custom component from scratch and add it in the library so that we can reuse it as an additional peripheral for the processor. In fact, there are two ways to add custom logic. The first is by using a dedicated GUI component editor that we're going to see in the next slide. The other is by using a Tcl script where you can describe your components using text and Tcl commands. These two steps make it possible to repackage custom logic for IP reuse, meaning that it's possible for designers to reuse their custom design as an additional peripheral. So this slide here shows the principle of the component editor. Adding custom logic with a GUI interface requires, in fact, 4 steps. The first step consists in adding your HDL design file to the tool. Then, a second step here maps the different signals to the bus signals of the Avalon interface. The third makes it possible to add transaction timing settings to make sure that the constraints are met. Finally, you can build your own package for your IP in order to reuse it later. After describing your design in hardware, it is possible to get the software development project, which is another tool. This consists of an integrated environment where you can describe your application in C or C++ or even in assembly code if you want. If you're not too familiar with this tool, it's possible to start from a template or with an example. There are a lot of examples that are provided. Then, all network stacks, file systems, graphics libraries, and software packages are automatically provided by the tool according to the SoPC file that has been generated in QSys, remember? All peripherals come with their drivers, or at least provide helpful tools to develop them. Furthermore, it's also possible to use an operating system. By default, the MicroCOS2 operating system is provided with all its libraries, drivers, API, and it's very, very easy to use it. At Intel, the software development tool is called SDK, and it comes with a source editor, compiler, a debugger, profiler, flash programmer, etc. You have the possibility to develop your application very fast, as you will see during the lab. So the Neos 2 SDK software come with 2 flavors. The first one consists in using command shell by writing scripts, sending commands within a terminal. The second flavor is an Eclipse-based IDE, which is more user-friendly, but can do exactly the same thing as the Neos 2 command shell. The Neos 2 software build tools also feature a compiler that makes it possible to compile your own application, but also the BSP, which is the board support package. This BSP consists of a library of functions that are used to manage the different peripherals that you're going to use in your system. The Eclipse environment makes it possible to easily manage your project by adding your own source files. The tool comes with software templates, which consist of very easy to use examples where you can learn how to manage different peripherals, how to interact with your operating system, and how to write specific functions for hardware management. Finally, the associated BSP project is also very simple and can be easily configurable to customize hardware to your needs. Well, we have studied so far the Intel Design Suite. Now we're going to take a look at the embedded system development in Xilinx, and you will see that the tools are quite similar in their principles. In this slide, you see here the Vivado tool from Xilinx. This tool is equivalent to the QSys plus the Quartus software. It means that it manages the description of a system and generates the corresponding HDL files for hardware implementation. Everything can be handled within the same tool, and the microprocessor system can be built by taking components from the library and connecting these components with each other, just like in QSys. The methodology here is quite similar to the previous methodology that we studied. After describing the requirements and the specification of the system, the system design step consists in partitioning what is going to be implemented in software and what is going to be implemented in hardware. The hardware development is performed using Vivado, as we've just seen. All system design, IP integration, interfacing, flow planning, implementation, and test are performed in Vivado. In parallel, designers may develop their own software using another tool called SDK, again, where they can build their own application, board support packages, OS integration, and manage how to interface software with hardware. The last step consists of system integration and final testing. After that, it's then possible to implement the full design in an FPGA. The bitstream file is first downloaded to the FPGA in order to download first the processor and the peripherals and all the hardware blocks in the circuit. And once this is done, it's possible to download your application software in memory, where the code will be found by the processor to execute your application. As you may see, although the tools are not exactly the same in both Xilinx and Intel, the principles remain the same. And if you're able to understand and get familiar with one of these tools, then you won't find too complicated to go from one tool to another. Well, that's it for today. Thank you very much for watching this video. I really hope that you appreciated it and learned new things about FPGA. So thank you again, and see you soon.